We're now going to look at Newton's third law, and the third law is a lot different from the other two. Now, when you look at Newton's third law, it says when one body exerts a force on a second body, so say for instance you've got an object A exerting a force on B, then the second body B will exert a force equal in magnitude in the opposite direction on the first body. So if A is exerting a force on B, B will be exerting a force on A that will have equal magnitude but be in the opposite direction. So what's very important is these two are not working on the same object. It's A on B and B on A. Now it sounds very easy, but when you start to apply this, you sometimes make mistakes. So let's look at this. We've got this girl sitting on a chair, and now I ask you to name the reaction force, right? Action, reaction force of the girl's weight. Now, if you think about the forces working on this girl, you've got a gravity pulling her down, so there's a gravitational force, and then obviously there's the normal force of that seat pushing her up so that she don't sink in, right? So you've got those two, and they are equal because I know she's not going up or down, right? But when you're working with Newton's third law, that normal force and gravitational force can't be a pair, right? A Newton 3 pair is always working on different objects. So the one is working on B, the other one is working on A. So it's like man on crate, crate on man. They're always working on different objects. So those two can't be a pair, right? So let's just think, what is weight? Weight is the force of the earth on the girl, right? So if they ask for the reaction force of that, that should be the force of the girl on the earth, right? And remember, weight is downwards, right? So this will be a force upwards. It's always in the opposite direction. Now, you might have a problem with the fact that the girl is exerting an attraction on the earth. She's pulling the earth up, because you don't see the earth falling towards you, but you see the girl falling towards the earth. That is just due to Newton's second law. Right. If you have, for instance, a bug and a train, if the train is traveling and the bug is traveling and they connect, right, then the force of the train on the bug is equal to the force of the bug on the train. So that is the constant. That is the same for both of them, right? But the mass of the bug is very small, so it has a big acceleration, and the velocity is changing so much that it will be scattering limbs in all directions, while the train has got a big mass, and the mass is so big that the acceleration is so small that you won't even observe that, right? So here the girl is attracting the earth, but the earth has got a big mass, so you don't see it accelerating towards you, right? So if the force is the earth attracting the girl downwards, then the interaction force, the reaction force, should be the force with which the girl is attracting the earth upwards. Right, name the reaction force of the normal force. Now, what is the normal force? The normal force is the surface, or the chair in this instance, on the girl, right? So it is the force of the surface on the girl, and this normal force is working upwards, right? Surface on girl, or you could even have said, yeah, okay, normal force, surface on girl, or chair on girl. So what is the reaction force? What is the force in the opposite direction? That will be the girl on the surface, right? Or the girl on the chair. And that will be a downward force. So if it is surface on girl, then this is girl on surface. That one was earth on girl, so the interaction was girl on earth, right? So just make sure two forces acting on the same object can never be a Newton 3 pair. Newton 3 pair the pair act on different objects. Right, in the next one you will see, according to Newton's third law of motion, the cart exerts a force backwards on the horse, and that is equal to the magnitude of the force of the horse on the cart. So let me make an easier drawing. Right, if you've got the horse and you've got the cart and they are connected, then horse on cart and cart on horse, that will be the same. Right, so the horse pulling the cart, horse on cart, is equal to the force exerting backwards of the cart on the horse. Right, now they ask, do these forces give a near zero net force, and how is it possible for the cart to move? Now, yes, they are equal, but we never look at them together. When you look at the force, you look at the net force on an object. So you never look at both same times. Remember, this one is working on horse and that is working on cart. So what we need to do is only look at the forces working on the horse, or only looking at the forces working on the cart. Now, if you think about the cart, the horse is pulling it forward and there's a frictional force towards the back. So as long as the horse is pulling harder than the frictional force, you will have an F net in the forward direction and you will have acceleration. Right. The same thing is working from the horse as well. So the cart is pulling it back, but what's the horse doing? It is pushing backwards against the ground, right? So its hooves are pushing backwards, and therefore the ground will be exerting a forward. Right, so ground on hooves, hooves on ground. So the hooves on ground is pushing to the back and the ground on the hooves are pushing forward. So as long as that is bigger than the cart that's pulling back, you will have an F net in the forward direction and accelerating. So the important thing to say here to answer this is Newton 3 forces, like this horse, cart, cart, horse, are working or exercise on different objects. So they can't cancel out. You never look at them together, right? To determine if an object, a single object, move or accelerate, you need to consider, or need to find the F net on that object. Right. So when you look at Newton 3 forces, horse on cart, cart on horse, you will never consider them together, because to determine if an object, the horse or the cart, accelerate, you need to look at only the F net on that object. So here they'll definitely not cancel out, and they will be able to move because the net force on the horse will be in the forward direction and the net force on the cart will be in the forward direction. Now guys, that is all for Newton's third law. In the next video we will look at the universal gravitational law.